Chapter 4, the Laplace transform. So for this chapter, we'll talk about the definition of the Laplace transform, and then inverse transform and transform of derivatives, and then translation theorem. The definition of the Laplace transform. The differentiation and integrations are the transforms. And this is the another transform into another functions. So by definition, Laplace transform of f of t equals integral 0 to infinity e to the minus st times f of t. From here, basically, we're going to go from time domain to frequency domain. So as you can see, we need to multiply f of t times e to the negative st. That s equal to j omega. So the omega is the angular frequency, right? So we're going to turn this time domain function into j omega domain, which is s domain, which is frequency domain. And the result of the function is in terms of s. What is a s? Again, it is j omega. And this is the one of the many techniques to solve the differential equations. You will see later sections that we can use this Laplace transform to solve the differential equation. And it's going to be much easier than what we learned in chapter 3. Let's find the Laplace transform of 1, just using the definition. So from the definition, we said Laplace transform of f of t equals 0 to infinity e to the negative st f of t dt.
Hey, Dr. Kim, I see the integral 0 to infinity. What about, can we go to the negative side?
Yeah, we can do that. So in the definition, also we can say negative infinity to positive infinity. But just for the sake of the simplicity, and in this class, we're going to talk about only positive side. And it is what we call unilateral definition. So from this definition, we're going to put that in here. So 0 to positive infinity, e to the negative st. What is our f of t? That is 1 and dt. So we need to have a 1 over negative s, and then e to the negative st, and going from 0 to infinity. And that is 1 over negative s. If you plug in positive infinity, e to the negative s times infinity, minus e to the s times 0, negative 1 over s. So 1 over e to the s times infinity minus 1. 1 over e to the s times infinity. S times infinity is going to be really huge number. So that is 0 minus 1. So the answer is 1 over s. So if you take the Laplace transform of 1, it's going to be 1 over s. Second example, let's do 1 plus 5t. So the Laplace transform of 1 plus 5t, Laplace transform of 1 plus Laplace transform of t. We can take a 5 to the front, that's the constant. So we already did Laplace transform of 1. So let's take a look at Laplace transform of t. From the definition, we have integral 0 to infinity t times e to the negative st dt. So we need to do the integration by parts. So we're going to say u equals to t, and then dv equals e to the negative st dt. From dv to v, we have negative 1 over s, e to the negative st, u to du is just simply dt. And then we multiply this, that equals u v t negative 1 over s, e to the negative st, 0 to infinity, minus integral v du, negative 1 over s, e to the negative st dt. Just copy one more time. T times negative 1 over s times e to the negative st, 0 to infinity, plus 1 over s, negative 1 over s, e to the negative st, 0 to infinity. The first term, I'm going to take out 1 over s out. And then if you plug in infinity, infinity times e to the negative s times infinity minus 0 times e to the negative s times 0 minus 1 over s squared with e to the negative s times infinity minus e to the negative s times 0. So the first term, infinity times e to the negative s times infinity, this guy is going to be 0. So this whole thing is 0. The second term is 0. So this whole term is going to be 0. And then we know this is again 0 and this is 1. Therefore, it is 1 over s squared. So now we know Laplace transform of t equals 1 over s squared. So we have 1 plus 5t, we end up getting 1 over s plus 5 over s squared. You take the Laplace transform of t, we have 1 over s squared. So 5 times 1 over s squared, which is 5 over s squared. Let's do this. The definition of the Laplace transform is this. So when you plug this in, Laplace transform of f of t is now 0 to infinity e to the negative st times we have e to the negative 2t minus 5 and dt. And we can separate that e to the st times e to the negative 2t times e to the negative 5 dt. This term is the constant. So e to the negative 5, 0 to infinity. E to the can take out negative sign and then s plus 2 and both has the t right there and dt. So now we can take the integral e to the negative 5, 1 over negative s plus 2 and e to the negative s plus 2 t 0 to infinity. Similar way, if you plug in infinity, e to the negative s plus 2 times infinity minus e to the negative s plus 2 times 0. This guy is going to be 0. So e to the negative 5 over negative s plus 2 and 0 minus 1, which is e to the negative 5 over s plus 2. F of t equals e to the negative 2t minus 5, right? E to the negative 2t times e to the negative 5. And when you take the Laplace transform of this guy, this is the constant. So we have that constant. And this e to the negative 2t transformed into 1 over s plus 2. So this is the last problem that we're going to use the definition of the Laplace transform. Now, just like I showed you from the first one, Laplace transform of the 1 equals 1 over s. If you have a Laplace transform of t, we're going to have a 1 over s squared. If you have a Laplace transform of e to the negative 2t, 1 over s plus 2. I gave you this table. If you look at a handout equation sheet, you should be able to see the Laplace transform pairs. 1 to 1 over s, t to the power of n to n factorial over s to the power of n plus 1. Laplace transform of e to the at, it is 1 over s minus a. Sine kt to k over s squared plus k squared, cosine kt s over s squared plus k squared. So you don't have to remember any of those. The table for the Laplace transform is given, so you know how to use them and find the right pairs. Let's do this. T squared. So we have a t to the n and say t to the n is going to be n factorial over Sn plus 1. T squared then, we have a 2 factorial, a2 plus 1 plus transform of f of t now equals, the first one is what? 2 over s cubed. E to the negative 9t is 1 over s minus a. So it is 1 over s minus minus 9 plus 9. And the 5, the constant, is 5 over s. Last one. Cosine 5t plus sine 2t. So from the table here, cosine kt is s over s squared plus k squared, and sine kt equals s squared plus k squared, and the numerator is going to be k. So first cosine 5t s at the numerator, and then denominator s squared plus 5 squared, which is 25, plus for the sine denominator, it's going to be s squared plus 2 squared, which is 4. For the numerator, just k, which is 2. So we are going to use this notation. Lowercase f always is time domain, lowercase y, time domain, lowercase x, time domain, uppercase f, s domain, uppercase y, s domain, uppercase x, s domain. So going from lowercase to uppercase, that's the one change from Laplace transform in S domain versus T in the time domain. And also, you need to be careful by writing S. It's because we're going to use this S as a S domain. And I have seen some students, when you solve this type of a problem, now you confuse yourself and write S as something like this, and you interpret that as a 5. Be careful with the S when you're writing S. Nice curve, and when you write 5, something like this.